Right. Hello, everybody. This is our lecture 5 in the series of Unit 3 content of digital communication as per IPU syllabus. And in this class, we will be covering the concepts of intersymbol interference, what this means, what this entails, what is the main reason, how can we remove it, what are the criteria to do that. And we will also be talking about um, the essential idea that why intersymbol interference is an unavoidable error, right? So this is what is going to be lecture 5. So let's get on with it. See, intersymbol interference, obviously the word means that there are two symbols which are interfering with each other. The point is, first of all, let's build upon that. Let's build upon the idea of what we understand by symbols, and then try to understand how that interference comes into the picture. So for that, let's first of all look at a block diagram of a communication system. तो हमारा जो ब्लॉक डायग्राम कम्युनिकेशन सिस्टम्स का होता है वो कुछ ऐसा होता है कि आपके पास डेटा होता है, आपका डेटा ए टू डी में कन्वर्ट होता है. दिस इज डेटा, राइट. एनालॉग टू डिजिटल फॉर्म में डेटा कन्वर्ट होता है. एनालॉग टू डिजिटल फॉर्म में कन्वर्ट होने के बाद नॉर्मली हम उसके ऊपर डिफरेंट किस्म की प्रोसेसिंग्स लगाते हैं, जिसका मतलब सोर्स कोडिंग, चैनल कोडिंग, एंक्रिप्शन. सो दिस गोज थ्रू अ प्रोसेस ऑफ various processings to give us the final bit stream. And normally, this bit stream is met with a line code, right? It's met with a line code. Now, this particular line code is important in the sense that this line code contains the electrical representation of the data. And what we have studied in unit 4, or what we study in unit 4, is that beyond that electrical representation there is a possibility of overlapping a higher frequency, the carrier frequency on the onto the data. And essentially what that does is that it prepares the data for long range communication as modulation does. So वो हमारा बैंड पास मॉड्यूलेशन के मेथोडोलॉजी के अंदर रिस्ट्रिक्ट हो जाता है, वहाँ पे उसकी मीनिंग आ जाता है. तो उसको उस लिहाज से समझा जा सकता है. So normally you apply a layer of modulation along with this, and that goes forward. But the problem, as we were talking about the intersymbol interference issue, that is somewhere here. So the main issue where the intersymbol interference logic is going to happen is the channel. What is happening in the channel, and why is it that uh, we get interference between the transmitted symbols is the main crux of the question. So normally what would happen is that there will be a sequence of receiving structure. That receiver will be a filter or things like that. हमने ये सारे अभी पढ़ लिए हैं. तो थर्ड यूनिट के फर्स्ट चार जो हमारे वीडियोस थे उसके अंदर हमारा रिसीव्ड डेटा का जो लॉजिक है वो एक्सट्रैक्ट करने का फंडामेंटल था. एंड फाइनली यू एक्सट्रैक्टेड बिट स्ट्रीम जो है that goes through a D2A converter and you get your data back, whatever is the estimated or the best possible data extraction that is possible. So that is the main idea. That is the main idea that is going on, right? Now the main question here is, I said that there is a problem that happens in the channel. So and we are not talking about AWGN, we are not talking about additive white Gaussian noise here. What we are talking about is the problem that we face when um, even if there is no noise there, even if there is no extra noise that is happening into the system, the channel is going to create some sort of a noise. So the question over here is what is happening there. So let's try to have a look. Okay. Well, the first thing that we need to understand is that आपका जो भी लॉजिकल डेटा का लाइन कोड होता है, आपका 10110 किसी भी किस्म का आपका बिट स्ट्रीम होगा, उसकी रिप्रेजेंटेशन रेक्टेंगुलर वेव्स के तौर पे हो रही है। रेक्टेंगुलर मैं इसलिए बोल रहा हूँ क्योंकि ज़रूरी नहीं है कि वो स्क्वायर वेव्स हों। स्क्वायर वेव्स का इंटरप्रिटेशन कुछ इस तरीके से ले लिया जाता है जिसके अंदर एम्पलीट्यूड और टाइम लाइन थोड़ा स्क्वायर जैसा सा स्ट्रक्चर बनाते हैं। मैं रेक्टेंगुलर वेव कह रहा हूँ, आप उन्हें ब्लॉक वेव्स भी कह सकते हैं, आप उन्हें स्क्वायर वेव्स भी कह सकते हैं, बट रिप्रेजेंटेशन सडन चेंजेस इन एम्पलीट्यूड के बेसिस पे मॉनिटर करी जाती है। अब वो +1 और 0 के बीच में हो सकता है, +1 और -1 के बीच में हो सकता है कि +1 हाफ टाइम पीरियड से रिप्रेजेंट किया जा रहा है, हो सकता है +1 पॉजिटिव हाफ से नेगेटिव हाफ के ट्रांजिशन में रिप्रेजेंट किया जा रहा है। अलग अलग किस्म के लाइन कोड्स में हम ये सारा डेटा देखते हैं, बट इन एनी केस द इंफॉर्मेशन इज अंडरस्टूड in the form of block, in the form of a data that is converted from a rectangular way. तो इस इंटरप्रिटेशन को यूं भी समझा जा सकता है that these are nothing but impulses. मैथमेटिकली हम इस तरीके से इसको कर सकते हैं कि these are individual impulses that are convolved with a singular block, right? These are consecutive impulses which are convolved with a single block wave, all right? Now, the main idea behind this logic, why are we choosing it like this, is to get a better idea of the frequency representation of the structure. आप याद रखेंगे कि लाइन कोड अपने आप में एक रैंडम प्रोसेस है। रैंडम प्रोसेसेस का कोई एक डिफाइंड फोरियर ट्रांसफॉर्म नहीं होता, ठीक है? तो अगर रैंडम प्रोसेस का कोई एक फोरियर ट्रांसफॉर्म डिफाइंड नहीं है, तो हमें उसके पावर स्पेक्ट्रल डेंसिटी के पॉइंट ऑफ व्यू से समझना पड़ता है। पावर स्पेक्ट्रल डेंसिटी का कॉन्सेप्ट जो है वो हमारा मेनली ऑटो कोरिलेशन फंक्शन और उस तरीके से निकल के आता है, जो कि अगेन एक लंबी चौड़ी कहानी है, वो उसके बारे में अभी बात करने का कोई मतलब नहीं है। बट हमें कुछ आइडिया लगाने के लिए कि ये बिहेवियर कैसा जाने वाला है, हमें थोड़ा सा ये वेव का स्ट्रक्चर हेल्प करेगा। तो इवन इफ अगर मैं अज्यूम कर लूँ कि मेरा पावर स्पेक्ट्रल डेंसिटी ऑफ द गिवन वेव जो है वो एक लिमिटेड रेंज में ख़त्म हो जाता है कैसे भी करके, राइट? द अदर पार्ट ऑफ द स्टोरी, नॉर्मली पहली बात तो आप याद रखेंगे पावर स्पेक्ट्रल डेंसिटी जो है, अगर मेरा लिमिटेड ऑटो कोरिलेशन का सीक्वेंस है तो मेरा पावर स्पेक्ट्रल डेंसिटी जो है वो इनफाइनाइट वेव का होगा। याद रखेंगे कपल ऑफ थिंग्स, पावर स्पेक्ट्रल डेंसिटी पीरियोडिक तब होता है जब सिग्नल पीरियोडिक होता है। जब सिग्नल पीरियोडिक होता है पावर स्पेक्ट्रल डेंसिटी पीरियोडिक होती है, और जो उसका आई एम सॉरी, जब सिग्नल पीरियोडिक होता है तो ऑटो कोरिलेशन पीरियोडिक होता है। जब ऑटो कोरिलेशन पीरियोडिक होता है तब आपका जो पावर स्पेक्ट्रल डेंसिटी है वो आपके इम्पल्सिस के वेव में आ जाता है। अगर आपका टाइम में इनफाइनाइट ऑटो कोरिलेशन फंक्शन है, ऑब्वियसली ऑटो कोरिलेशन टाइम डिफरेंस पे होता है, तो आप यूं भी कह सकते हैं कि टाउ में अगर इनफाइनाइट का फंक्शन है तो पावर स्पेक्ट्रल डेंसिटी जो है वो आपकी फाइनाइट फ्रीक्वेंसी बैंडविड्थ की होती है। तो सबसे पहली चीज़ समझनी ज़रूरी ये है कि प्रैक्टिकल सिग्नल्स कभी भी इनफाइनाइट टाइम ड्यूरेशन का ऑटो कोरिलेशन नहीं रख सकते, क्योंकि उनके बीच में टाइम डिफरेंस का जो इफेक्ट है कहीं ना कहीं नेगेट हो जाएगा। आप यूँ समझ लीजिए कि अगर एक सिग्नल यहाँ से शुरू होकर यहाँ ख़त्म हो गया और आपको इसी के साथ कोरिलेट करना है, तो इसकी टाइम लाइन कभी भी इनफाइनाइट नहीं हो सकती, है ना? और हमारे प्रैक्टिकल सिग्नल्स का हमेशा एक स्टार्टिंग और एंडिंग पॉइंट होता है। इसीलिए जो पावर स्पेक्ट्रल डेंसिटी है वो कभी भी प्रैक्टिकल सिग्नल की थियोरेटिकली यूँ नहीं कहा जा सकता कि फाइनाइट होगी, हमेशा उसकी पावर स्पेक्ट्रल डेंसिटी इनफाइनाइट होगी। फर्दर जो हमारा ये स्क्वायर वेव आपने लिमिटेड वाला लिया है, इसकी जो पावर स्पेक्ट्र इसका जो फ्रीक्वेंसी स्पेक्ट्रम होगा वो होगा सिंक वेव के तौर पे, जो अगेन एक इनफाइनाइट सीक्वेंस है। टाइम में कॉन्वोल्यूशन का मतलब यहाँ पे मल्टीप्लिकेशन होगा, सेंटर का पॉइंट इलेबोरेट हो जाएगा, हाई हो जाएगा, और जो साइड बैंड्स हैं वो डिमिनिश होते चले जाएंगे लेकिन ज़ीरो नहीं होंगे, राइट? उनकी कुछ ना कुछ एग्जिस्टेंस हमेशा रहेगी। मैं फ्रीक्वेंसी के बारे में इतना स्ट्रेस क्यों दे रहा हूँ? क्योंकि यहाँ समझना ज़रूरी है कि जो भी सिग्नल हो, irrespective of what line code you are using, it's going to have an infinite bandwidth to get represented originally. Original representation के लिए it will have to have infinite bandwidth. Alright? अब एक बार ये एस्टैब्लिश हो गया, तो हमें ये भी पता है कि जो ये चैनल है वो इनफाइनाइट बैंडविड्थ को तो सपोर्ट नहीं कर सकता। इसका मतलब ये है कि चैनल किसी ना किसी रेंज ऑफ फ्रीक्वेंसीज में ही ऑपरेट करेगा, ना उसके बियॉन्ड वो चैनल एक्सेप्ट कर पाएगा, ना प्रोजेक्ट कर पाएगा, और उसकी बैंडविड्थ के बेसिस पे रिसीव्ड सीक्वेंस जो है आपका डेटा को कैप्चर करने की कोशिश करेगी। इसका मतलब है कि जो हमने एक बड़ा सा इनफाइनाइट वेव, इनफाइनाइट फ्रीक्वेंसीज का सिस्टम लिया था, वो अचानक से ब्लॉक हो गया, अचानक से कर्टेल हो गया। इसकी ब्लॉकिंग होते ही हमारी इशू ये आ जाता है कि आपका जो साइड बैंड स्ट्रक्चर है वो खत्म हो गया, और आपके पास सिर्फ एक फिक्स फ्रीक्वेंसी रह जाती है, एक फिक्स फ्रीक्वेंसी रेंज रह जाती है। जो फिक्स फ्रीक्वेंसी रेंज रह जाती है, इसकी रिप्रेजेंटेशन कभी भी किसी भी बिट के लिए ऐसी नहीं रहेगी जैसी रेक्टेंगुलर की होती है। इट विल फेस सम सॉर्ट ऑफ अ रोल ऑफ, right? And because it has been limited in frequency, every representation will have infinite timeline. Obviously it will diminish to some quantity, but it will have infinite timeline. So what happens is that even in the representation of a simple bit stream like this, where the data was supposed to be only something like this, the representation structure goes infinity for the first one, then you have some sort of zero representation also going somewhere like this, then one representation also diminishing like this, and another one representation like this, and you have a lot of messy data. And what happens because of this messy data is that, just a second please. So what happens because of this messy data is that your received bits 10110, instead of coming like a proper waves like this. Sorry, that's a horrendous diagram. Just a second. Yeah. Instead of coming like this, the waves get received something like this, right? There may be interference that causes a certain bit to get damaged. This is called intersymbol interference, because there is so much data that is getting overlapped about each other, that it becomes a very serious issue to deal with. So I hope you are able to see this, that intersymbol interference in that sense is an unavoidable error till the time line codes are being used as they are. Of course, the use of line code is a very specific thing, because line codes serve much more purpose in the sense that in ease of application and many other things. And even in the extension towards ASK, FSK, PSK, we have seen that line codes play a crucial role. So the main concern here is that what happens when you are using, or what criteria should be there such that the intersymbol interference is either minimized or removed, right? Hence comes in the contribution of the scientist Nyquist. So Nyquist published a criteria regarding intersymbol interference, and the rule of Nyquist was that to avoid intersymbol interference, what one needs is that there are two conditions that need to be satisfied. The first condition is uh, how do we? Yeah. So the first condition is that the wave representation, the representations of ones and zeros, should be done in such a fashion that you have a wave called PT, right? And PT should be equal to PT should satisfy this criteria. Yes. PT should satisfy the criteria that, and notice that I am writing PT, so that means it's a continuous wave. It means it's a continuous wave. It is important to note here that we're talking about a continuous wave. Just let me. Right. So the criteria it needs to meet is. So for t is equal to 0, the wave needs to reach its maximum constant value. We are writing 1. This can be any constant, any pre-decided constant for that matter. Doesn't really matter. So this pre-decided constant may be a in our case, right? And for t is equal to ntb, that is bit period multiple time, the data should always reach 0. Okay, the data should always come down to 0 when the pulse is like that. That's the criteria that Nyquist suggested. Second thing that he suggested was that PT should have minimum bandwidth, right? So obviously we require the bandwidth to be limited, because if it is not going to be limited, then again intersymbol interference is going to happen. So we should have minimum and limited bandwidth. Okay, it should not be of theoretically infinite wave. It should be a wave which is of infinite time, right? But follows the criteria as mentioned over here, and should have the minimum bandwidth. Well, that's easier said than done. So Nyquist also proposed his own wave, right? Nyquist proposed that, let's understand the logic as something like this. For an entire digital communication system, let's say that the composite nature of what is coming in is h of f. Now, what this means is that if you have h of f, it is a contribution of three components. You have ht of f, you have hc of f, and you have hr of f, right? What we mean by this, what we mean here by this is that we have a big block which is called h of f, right? And the input to this h of f are impulses that represent ones or zeros. So these impulses kind of give you an output in the form of structured pulses. I'm making the pulses in the form of what we would require, but this gives you the structure in the form of pulses. What is happening here is that these particular inputs are going through the process of transmission, going through the process of channel, going through the process of reception, and finally, once all of the data is cleaned and the noise removed, the data is received in the form of structured pulses. And these pulses can then be put into the detector side where they can be decided as high or lows. So the main idea is that HT, HC, HR are combined. That is the effect of the transmitter, the channel, the receiver are combined together to create one definition of a transfer function called h of f. And whatever definition is going to be given for h of f, it is going to be considered the shape that the pulse is supposed to be getting, right? Because the idea is that I require such a shape at the very end so that when I make the decision, I'm able to take the decision on the basis of whether the data over here was high or low. That's the only concern. Okay. So in between, a lot of stuff can happen. In between, everything can go wrong. But still, if I'm able to recover the data in this form, I don't care. Okay. So now let's give it a shot. Also, I would like to mention here that since this is ट्रांसफर फंक्शन एच ऑफ एफ, अगर मैं इसका फोरियर इनवर्स ले लेता हूँ तो एच ऑफ टी एसेंशियली जो है वो आपका इम्पल्स रिस्पॉन्स होगा, क्योंकि मैं ये सिस्टम का इनपुट ही इम्पल्स मान रहा हूँ, तो जो भी मैं यहाँ पे आउटपुट एक्सपेक्ट कर रहा हूँ वो और कुछ नहीं, सिंपली एच ऑफ टी ही होगा। तो यहाँ पे एच ऑफ टी और पी ऑफ टी की डेफिनेशन सेम ही है, यानी कि एच ऑफ टी की जो नेचर है, जो एक्सपेक्टेशन है वो यही है कि वो पी टी को इस तरीके से सेटिस्फाई करेगा, ये कंडीशन उसे सेटिस्फाई करनी चाहिए। अब जैसे मैंने कहा कि नाइक्वेस्ट ने एक सॉल्यूशन ऑलरेडी प्रपोज कर दिया था, सो लेट्स टॉक अबाउट दैट सॉल्यूशन। नाइक्वेस्ट प्रपोज अ सॉल्यूशन दैट why not take h of t as a gate pulse. So what he suggested was that, I'm sorry, not h of t as a gate pulse. He suggested why not take h of f as a simple low pass filter. The question was, if it is a low pass filter, what should be its bandwidth? Well, since we require that the system should have minimum bandwidth, let's consider the minimum bandwidth. So the idea is that he suggested that h of f be made into a low pass filter, and the bandwidth should be the minimum possible bandwidth. The theoretical minimum bandwidth of any given system is RB by 2, right? So theoretical minimum bandwidth of the system is RB by 2. And this may have some sort of a positive amplitude A, right? So the idea is, once you have the logic of minus RB by 2 to RB by 2, when you take the Fourier inverse of this, what are you going to get? So when you take the Fourier inverse of this, always remember that the entire range for which this block is going to carry on, that is going to be the total. If you take the total and you invert that, that total is going to be where the main lobe is going to touch the axis, the x-axis, and multiples of that particular element, that value is going to be where all the oscillations are again going to meet the value 0 or meet the x-axis. So in this case, that data would be time tb. You can imagine that it is minus rb by 2 to rb by 2. Add that, so you have tb, you have rb, invert of that is tb. So माइनस टीबी टू टीबी के बीच में आपका जो सिंक वेव है वो एक पॉजिटिव मेन लोब लेके आएगा, एंड देन फॉर एवरी फर्दर मल्टीपल आपका डेटा जो है वो जीरो पहुंचता जाएगा। ऑलराइट, सो दिस सेटिस्फाइज द कंडीशन ऑफ नाइक्विस्ट दैट ये जो डेटा है ये हमेशा मेरा एवरी मल्टीपल ऑफ टाइम पे जीरो वापस जीरो पहुंच जाना चाहिए, सिवाय टाइम टी इज इक्वल टू जीरो के। अब ज़रा इसे समझना बहुत ज़रूरी हो जाता है कि ऐसा नाइक्विस्ट ने क्यों कहा और इस क्राइटेरिया का सेंस क्या है। तो अगर मैं इसे पी टी या एच टी ले लेता हूँ तो ये मेरा मेन सीक्वेंस हो गया, ये मेरा डेटा हो गया, और ये जो मेन डेटा जो मेरा इम्पल्स रिस्पॉन्स है ये हर एक इम्पल्स के ऊपर कॉरेस्पॉन्ड करेगा। ठीक है, अब यहाँ पे अगेन एक बहुत ज़रूरी एस्पेक्ट आ जाता है कि मैं आपको अपनी तरफ से कोशिश करके एक अच्छा डायग्राम बना के दिखाऊं कि इसका मतलब क्या है और कैसे नाइक्विस्ट क्राइटेरिया एक्चुअली हमारी हेल्प करता है। ठीक है, सो लेट मी ट्राई। So as this will require a little precision and I'll try my best. So let's say that you have two impulses, all right? One impulse is at time t is equal to 1, of course, and the second impulse, time t is equal to 0 and time t is equal to 1. So these are two impulses here. Let's take a red pen now. And for the first impulse, what happens is that this sequence goes down like this. and at time t is equal to 2, 3, it always goes back to 0. Okay. Now you have another impulse, a gate, shifted impulse. When you convolute the same pulse train, the convolute the same pulse with this shifted impulse, there is going to be a replica of the same pulse shape that is going to be created. Let's try to draw that in another color. Let's take green, right? So what you're going to have is that there is going to be a main lobe between 0 and 2. The data is going to go to 3 and shift like this, right? So what you can see here is that at this point, there is no other contribution of any other wave. So the contribution of wave represented by represented at time t is equal to 1 is 0 at this stage. Similarly, the contribution of the red wave at t is equal to 1 is 0. If I take another impulse train, let's say a negative one, okay, and you try to make an orange wave for that. So what is going to happen is that a wave is going to exist between 1 and 3. It is also going to go down at 4, and something like this is going to pop up. So the idea is that no other wave is going to contribute towards the decision point at t is equal to 1, right? At the decision point of t is equal to 0, no other wave is going to be contributing except for the red one. At t is equal to 1, only the green one will be contributing. At t is equal to 2, only the orange one will be contributing. It is, what it means is that net design, even if my net representation goes something like this, even if the data goes something like this, right? At time t is equal to 0, when I sample stuff, I'm not going to use the whole data. I'm going to sample this data. So when I sample this data, what is going to happen is that I'm going to get the information at this point only. And this point's contribution was only from its wave that was meant to be there, and that was PT. Similarly, at this point, the data that I'm going to get is only what was contributed by the wave that existed here. Similarly, at this point, it is going to be only for this one. So rest everything is discarded, since we are going to sample the data anyways for decision. And hence, if we use a pulse that follows the criteria mentioned by Nyquist, what happens is that the entire intersymbol interference possibility is removed. It is diminished, it is over. What is the problem then? Go ahead and use it. The problem lies in the fact that these are infinite waves. PT is an infinite wave, and an infinite wave does not exist. I cannot have an infinite wave. Specifically, even if we say that we start the wave and it goes on till infinite time, we're never going to switch it off. But there is some point where you switched it on. कोई भी वेव उसको ऑन करने से पहले एग्जिस्ट नहीं कर सकती, जिसका मतलब ये है कि देर इज नो वेव दैट एग्जिस्टेड एट माइनस इन्फिनिटी टाइम, and hence it is impractical to state that there is any sort of infinite waves that are possible. And since infinite time is not possible, that means that the wave is going to be of finite time, hence infinite bandwidth. So there is going to be some sort of frequency that is going to exist for, uh, there is going to be some sort of frequency that is going to exist for components that are going to exist for infinite frequencies. A little jumbled up. Okay. So what is the idea? What is the criteria? How do I do this? So what we do is that there are now this entire theory that you've just understood is called intersymbol interference. How the books define intersymbol interference is that when one symbol spreads and smears into the decision boundary of the consecutive or other symbols. That is how the books define it. So the idea is very simple, that when one of the symbols spreads and this space where zero's decision was supposed to be taken, it spreads into that decision area, right? And it contributes to the amplitudal shift that zero is going to face. And that is what is intersymbol interference. So what you have understood here, I hope that you have understood here, is the concept of what is called as intersymbol interference. Now there are two methods, two schools of thought, which deal with the methodology of reducing or eliminating intersymbol interference. One of them involves a little bit of what you can say sacrifice of bandwidth. So the sacrifice of bandwidth, what it says is that let's stick to the idea of eliminating intersymbol interference, but let's try to reduce the restriction on the bandwidth. That is, use a little bit of excess bandwidth. So this concept is leads to the idea of curtailed sideband logic for the waves that we have, that is the PT waves that we have, and some sort of roll off criteria that exists, that is excessive bandwidth usage that exists in the idea of the low pass filter representation of h of f. ठीक है, तो आइडिया कुछ ऐसा है कि अ, इसको जो इस प्रोसेस को और ये फैमिली ऑफ कर्व जो हम पढ़ने वाले हैं, इन्हें रेज्ड कोसाइन फिल्टर्स कहा जाता है। तो जो जो एच ऑफ एफ की रिप्रेजेंटेशन है वो रेज्ड कोसाइन फिल्टर के नाम से जानी जाती है। ठीक है, दूसरा मेथडोलॉजी है जो ये कहता है कि भाई बैंडविड्थ पे कोई कॉम्प्रोमाइज नहीं किया जाएगा, बैंडविड्थ तो कम ही रहेगी, बैंडविड्थ उतनी रहेगी जितनी मिनिमम जरूरत है, तो बैंडविड्थ में कोई सैक्रिफाइस नहीं डाला जाएगा। लेकिन हम यूं कह सकते हैं कि कुछ लिमिटेड अमाउंट ऑफ इंटर सिंबल इंटरफेरेंस को हम आने दें। हम अज्यूम कर लें कि वो छोटी मोटी इंटरफेरेंस आएगी, और क्योंकि हमें पता है कि वो इंटरफेरेंस आने वाली है, इस वजह से हम उसको पहले ही प्री कोड कर लें, यानी कि उसकी एक्सपेक्टेशन में हम उसकी एनकोडिंग ऐसे कर लें कि जो डेटा जब रिसीव किया जाए तो उसे डीकोड करके, अज्यूमिंग के इंटर सिंबल इंटरफेरेंस हुई होगी, हम कुछ इंटरप्रिटेशन निकाल सकें और उस बेसिस पे हमारा जो रिकवरी है वो इंटर सिंबल इंटरफेरेंस से फ्री हो जाए। ये जो कॉन्सेप्ट है, जो स्कूल ऑफ थॉट है, इसे डुओ बाइनरी सीक्वेंसिंग एंड डुओ बाइनरी प्री कोडिंग के नाम से समझा जाता है। अभी फिलहाल हम रेस को साइन फिल्टर्स पे कंसेंट्रेट करेंगे, डुओ बाइनरी हमारा लेक्चर 6 होगा। तो बात करते हैं रेस को साइन फिल्टर्स के बारे में। तो ऐसा है कि रेस को साइन फिल्टर्स को समझने के लिए हम कुछ ऐसा करते हैं कि रेस को साइन का फॉर्मूला लिखते हैं। तो जी देखिए, मेन आइडिया रेस को साइन का क्या है कि रेस कोसाइन फिल्टर जो हैं, दे आर सपोज टू बी अ फैमिली ऑफ सच फिल्टर्स जो कि एक्सेस बैंडविड्थ को अलाउ करते हुए आपका जो फॉर्मुलेशन है, आपका जो टाइम डोमेन रिप्रेजेंटेशन ऑफ सिग्नल्स है, उसका मेन लोब ज्यादा इफेक्ट नहीं होने देते हैं, पर साइड लोब्स को एटेन्यूएट कर देते हैं। तो यानी कि आप किसी किस्म का रोल ऑफ अपने डेटा में इंट्रोड्यूस कर रहे हो, अपनी फ्रीक्वेंसीज में इंट्रोड्यूस कर रहे हो, जिसके बेसिस पे आप एक ऐसा मेथोडोलॉजी डिफाइन कर रहे हैं जो कि आपको कहीं ना कहीं एक कर्टेल्ड, एक रिड्यूस्ड साइड, जो आपका स्प्रेड है, जो साइड बैंड्स हैं, उनकी एक कर्टेल्ड रिप्रेजेंटेशन के तौर पे आपको दिखेगा। ठीक है, तो ज़रा फॉर्मूला लिख लेते हैं पहले, एंड फिर हम उसकी डिस्क्रिप्शन में जाते हैं। So we have h of f is equal to, अब ये इक्वेशन जो है ये करीब 3 पार्ट्स में डिवाइडेड है, करीब नहीं 3 पार्ट्स में डिवाइडेड है। लेट मी डिस्क्राइब दैट। 1, a little too ambitious. एक second, guys. This is all I need. So these are three parts to this equation. The first part, 1, and let me just write the equation first, and then I'll describe how it functions. Right. So let's understand this equation. There are three parts to this equation, and what I'm going to do is describing each part. I'm going to just plot all of them, one below the other, so one after the other. So that will give you the main crux of what has happened here, and why have we done that will be clear in just the next formulation that we write after this. So let's first draw what this means. First of all, the interpretation of the nomenclature. You see, there are two main things. Of course, F is the frequency. That's not one of the main ideas. There are two things. Is one is W naught and one is W. Here, W naught represents the minimum bandwidth, that is RB by 2, and W represents the actual bandwidth that is being used. Right? This is the actual bandwidth that is going to be used, and that is, of course, is going to be greater than or equal to W. Right? So there is a restriction on the excess bandwidth, and that restriction is 2W naught. That is, under any case, the transmitted bandwidth is not going to be greater than bit rate, right? And that is a reasonable assumption. The transmitted wave cannot be larger than the bit rate. That doesn't make any sense. So the frequency of switching cannot be made larger than already जो switching आप allow कर रहे हो, ठीक है? Bit rate से ज़्यादा bandwidth नहीं हो सकता. So these are the two restrictions. So it is going to be less than or equal to RB, and of course it is going to be greater than or equal to RB by 2. That's the restriction on W. So now let's try to understand how this particular function plots. So of course, for very first thing that you require is W naught. And since you are going to talk about positive and negatives parallelly, so you are also going to need minus W naught. Okay. I'm going to try to and make it to scale, but I may fail. So please bear with me. So this is going to be 2W naught, right? And minus 2W naught. And somewhere in the middle, somewhere between 2W naught and 2W naught is W. Let's assume that it is not so heftily away. Okay. Now, so what we say over here is that between the frequencies of 2W naught minus W. Now the question is, what is that? So 2W naught minus W is something like this, but from 0. So that will be a similar distance like this, but from 0. So a range of these points. And this is minus 2W naught plus W and this is 2w naught minus w. Okay, so for these values the data is 1. And next, for all values obviously greater than bandwidth, the data is 0. That much is established, no issues. Now the criteria, the main idea is what happens with this cos square. This is why it is called raised cosine. So very first thing that you note, cos square. What does that mean? Converted into 1 plus cos 2 omega. So what you get is 1 plus cos pi by 2 into the whole thing. Okay, 1 plus cos pi by 2 into the whole thing, whole divided by 2. That much is sure. And since cosine wave is going to be between -1 to +1, and you are adding a 1 dividing by 2, what that does is that the entire cosine wave is now shifting between 1 and 0, right? That is why it is a raised cosine. That's the first idea. Now, the shape between 2w naught minus w to w, of course, is going to be a cosine wave. That much is also sure. So the point is, how do we check the shape? It's going to be a cosine wave. It is going to be a wave that starts at a certain point, ends at a certain point, and that much is established. That's okay. So the point is, we have to see how the behavior is going to be. So the very first thing is put f is equal to 2w naught minus w in this equation. And as soon as you do that, you see cos square of 0. Cos square of 0 means that the data corresponds at this point, it corresponds to 1. यानी कि जो equality हमने यहाँ पे दोनों equations में use करी है, first part and the second part, that is fine. And similarly, the values over here are also 1. Negative के साथ वो parallelly चलेगा क्योंकि mod लगा हुआ. Next, put it to w. Put it at f is equal to w. As soon as you put that, you note that this converts into cos square of pi by 2. Cos of pi by 2 of course is 0, and that means this equality also holds. That the data is going to start at this point, end at this point. That much is sure. And of course, we know that it is going to have a curvature of cosine, and cosine starts from 1, goes to 0. So that wave is going to go like a cosine wave between 2w naught minus w to w. Then last question that remains is what is going to be the point of w naught? What is the value that is going to exist at that point? And when you check it, you observe that cos square, cos square pi by 4 multiplied by w naught minus 2w naught, so w minus w naught रहेगा. Numerator and denominator gets cancelled. So you have cos square pi by 4 or half. So same half point at both these cases. So that means W naught essentially marks the middle point between 2W naught by W, 2 naught W naught minus W and W. It marks the middle point between these two values, which is of course true. अगर आप W minus this point करके half करेंगे, so what you are going to get is W naught only, right? So ये इन दोनों का जो एवरेज निकल के आता है, आप इन दोनों को अगर ऐड करके by 2 करेंगे तो वो W naught ही आएगा. So essentially, this is going to be a cosine wave with the middle point as W. Okay. So ये जो point आएगा, ये half point है. अब आप देख सकते हो कि ये जो पॉइंट्स हमने टैली किए हैं, इनकी स्टार्टिंग और एंडिंग पॉइंट वेरी कर सकता है, लेकिन किसी भी पॉइंट पे किसी भी W की वैल्यू के लिए जो W नॉट का पॉइंट है वो वेरी नहीं करता है. ये पॉइंट पे हमेशा डेटा सेम रहेगा. अब अगर मैं W को W नॉट के इक्वल कर दूं, W को W नॉट के इक्वल कर दूं, तो होगा ये कि आपका जो कोसाइन वेव है वो खत्म हो जाएगा और ये एक आइडियल लो पास फिल्टर बन जाएगा. ठीक है, अगर मैं W इज इक्वल टू W नॉट कर देता हूं तो ये आइडियल लो पास फिल्टर बन जाएगा. अगर मैं W को बढ़ाता रहता हूं तो क्या होता है, सपोज अभी से भी ज्यादा बड़ा ले लेंगे तो जो उसका स्टार्टिंग पॉइंट है ना वो चेंज हो जाएगा और उसका रोल ऑफ जो है वो और आगे जाके खत्म होगा. This is looking a little messy. So in the meanwhile, what I'm going to do is I'm going to open MATLAB on the side. थोड़ा टाइम लगता है उसको खोलने में. As soon as it is open, I will uh, share some simulation in this regard with you. Okay, so ये idea है आपका raised cosine filter की property, and once we have established this idea, next what we can do is that we need to understand the time domain representation of this h of f. आफ्टर ऑल हमें तो जो यूज करना है वो एच टी है, ना कि एच एफ। तो हमें टाइम डोमेन में उसकी रिप्रेजेंटेशन का बहुत इंपॉर्टेंट यूजेज होता है। एक चीज मैं यहाँ पे इंटरजेक्ट करके ऐड जरूर करना चाहूंगा, और वो ऐड ये करना चाहूंगा कि जो आपका कई बुक्स में रिप्रेजेंटेशन जो है वो इस तरीके से नहीं लिखा जाता है। लेट मी टेल यू हाउ सर्टेन बुक्स टॉक अबाउट रेस कोसाइन फिल्टर्स। तो ये रेस कोसाइन फिल्टर्स का एक इंपॉर्टेंट डेफिनेशन होता है आर। आर इज कॉल्ड द रोल ऑफ फैक्टर, and the idea of R is that it is W minus W naught divided by W naught. Okay. Sometimes it is written in the forms of a form of a percentage. So there you can add 100 factor to that. So this much roll off percentage. What that means is that excess bandwidth percentage that is used. So of course, W equal to W naught is the minimum, so zero roll off, and W is equal to 2 W naught is the maximum, so one roll off. So that means R generally varies between 0 to 1 and can often be also represented in the form of a percentage. So 0 to 100%. Now, what that means is that there is a possibility of redefining the entire function in terms of only the roll off factor, and that is a pre-decided roll-off factor, that is the percentage excess bandwidth that we are prepared to use, and the minimum bandwidth or bit rate logic that is pre-decided also. So that kind of removes the ambiguity from these equations. They are equally valid to use, and since they are equally valid to use, what we are going to do is I'm going to rewrite this whole equation as many books would do it. Okay, and this, normally we would just remove this into 100, and this would imply that W is equal to 1 plus R into W naught. Okay, so this is what the interpretation is going to be used as. We put it over here, and what happens is that we can rewrite the whole thing. Let's rewrite the whole thing then. So the very first thing that you need to do is change the limits. So 2W naught minus W. Put W is equal to 1 plus R into W naught here. What do you get? So what we will get is that one W naught will get cancelled, and you will be left with 1 minus R into W naught. So to remove the ambiguity of what W naught is, what we do is that we use RB by 2. So essentially what will happen is that this is like 1 minus R into RB by into RB by 2, right? Similarly, this limit also is 1 minus R into RB by 2. Of course, W can directly be replaced over here, and this is 1 plus R into RB by 2. And finally, of course, 1 plus R RB by 2. Now let's put in the replacements over here. So the whole thing, the logic is basically just replace the same thing as we were doing over here. And what that would mean is that you will get minus 1 minus R, RB by 2, and over here w minus w naught. So this becomes a little bit more simpler in the sense that what you get is w minus w naught is simply put is w naught into r, or rrv by 2. Okay, so this is the overall formulation, and this is what is basically used. Sometimes the formula is also written in the form of tb instead of rb. That really doesn't matter. Essentially the idea remains the same. So I hope this structure that has been given to this entire thing is clear now. Okay. And now we will talk about the time domain representation of the same thing. What I'm going to stick to is first this one, the time domain representation, and then just convert it into the time domain representation for this thing, because there is just nomenclatural difference, nothing really major. So time domain representation, um, let us save the file. So time domain representation, HT, uh, it's a little involved, so please bear with me. Going to be in the form of a sync wave only. That means you have your twice w naught t, which essentially is nothing but t by tb. Okay, I'll show you how. You have this, and then you have a cosine structure divided by. So just a sec. This is your formulation. ये भयंकर सी फॉर्मुलेशन जो आपको दिख रही है इतनी कॉम्प्लिकेटेड नहीं है. मैं ज़रा आपको समझाने की कोशिश करता हूँ कि हम इसका इंटरप्रिटेशन क्या है. हम ऑब्वियसली इसके डेरिवेशन नहीं कर रहे हैं यहाँ पे, बट इंटरप्रिटेशन समझ लेना बहुत इंपॉर्टेंट है. तो जी सबसे पहले हम नोट करते हैं सिंक वेव. सिंक वेव जो है, इतना तो हमारा पक्का है कि जो सिंक वेव है आपकी, सिंक 2w0 का मतलब हो गया आर बी इंटू टी, और उसका मतलब हो गया टी बाई टी वी, जिसका मतलब है बेस फॉर्म में जो आपका सिंक वेव है ये वही है, और उसके साथ में कोई फैक्टर मल्टीप्लाई हो रहा है. तो यहां से एक चीज पक्की हो जाती है, 100% पक्की हो जाती है, कि सिंक वेव जिन जिन पॉइंट्स पे जीरो है, सिंक वेव जिन जिन पॉइंट्स पे जीरो जा रहा है, तो उस जब ये ऑलरेडी जीरो जा रहा है तो ये कुछ मर्जी हो जाए, कोई फर्क नहीं पड़ता, वेव पैरामीटर्स हमेशा जीरो जाएंगे ही जाएंगे. इतना तो पक्का हो गया. एक लौती जो चीज रह जाती है वो ये है कि ये जो मेन लोब का रिप्रेजेंटेशन है वो कैसा है, और बेसिकली इस कोसाइन लॉजिक का मतलब क्या है. देखिए कोसाइन के अंदर जब जैसे जैसे फ्रीक्वेंसी कोसाइन की बढ़ती, जैसे जैसे टाइम बढ़ता जा रहा है कोसाइन का, it is being downgraded by a factor, it is being reduced by a factor. And what it is being reduced by is essentially going to act as a quantity. सबसे पहली बात, जब आप इस सिस्टम की बात करते हैं, तो जैसे जिस जिस टाइमलाइन के बारे में यहाँ पे बात हो रही है, जैसे जैसे वो टाइम में कहानी आगे बढ़ती है, आपका जो फैक्टर है वो डिनोमिनेटर में इंक्रीज करता चला जाएगा, और जैसे जैसे वो फैक्टर बढ़ता चला जाता है, आपको ये भी नोट करना होता है कि जो उसकी वैल्यू है वो इक्वली आपके कोसाइन वेव के एम्पलीट्यूड की तरह उसे स्केल डाउन कर रही है. जिसका मतलब ये है कि अगर ये एक बेस सिंक वेव है, और अगर मैं नोट करूं कि टाइम टी इज इक्वल टू जीरो पे क्या सीक्वेंस चल रहा है, तो आप देख सकते हैं कि कोसाइन की बेस सीक्वेंस चल रही है, यानी कि टाइम टी इज इक्वल टू 0 पे डेटा 1 है। ठीक है, सिंक भी 1 है, मल्टीप्लिकेशन फैक्टर भी 1 है, तो ये तो पक्का हो गया कि यहाँ पे वेव 1। सेकेंडली, क्योंकि हमारा टी बी टाइम जो है, टी बी टाइम जो है, यानी कि माइनस टी बी से टी बी का जो टाइम है वो माइक्रो सेकेंड्स में होता है, तो उस वजह से ये कोसाइन वेव का जो फैक्टरल डिफरेंस यहाँ पे फर्स्ट लोब के अंदर होगा, बहुत ज़्यादा नहीं होगा, जिस वजह से जो इसका स्ट्रक्चर है वो मेनली ऐसा ही रहेगा। हाँ, जैसे जैसे ये टाइम में बढ़ता चला जाएगा, जैसे जैसे ये कहानी आगे बढ़ेगी, आप नोट कर सकेंगे कि this system is going to be multiplied by a damping cosine wave. This is going to be multiplied by a damping cosine wave. तो जो damping cosine wave है, ये धीरे धीरे इसकी मल्टीप्लिकेशन का लॉजिक कुछ ऐसा निकलेगा कि ये जो साइड लोब्स हैं ये अपने आप भी डिमिनिश हो रहे थे, और एक एडिशनल मल्टीप्लिकेशन फैक्टर भी आ गया उन्हें और डिमिनिश करने के लिए। तो मेन लोब की कहानी ऐसे की ऐसी रहेगी, और साइड लोब्स जैसे जैसे रोल ऑफ बढ़ता चला जाएगा, जैसे जैसे डब्ल्यू की वैल्यू बढ़ती चली जाएगी और स्लो होता चला जाएगा। जितना डब्ल्यू ज्यादा होगा उतनी जल्दी आपका ये नैरोइंग का सिस्टम शुरू हो जाएगा। तो इसलिए ये सिस्टम जो है, ये जो प्रोसेसेस हैं, इनको रेज्ड कोसाइन सिस्टम्स कहा जाता है, और ये अभी भी नाइक्विस्ट फैमिली ऑफ पल्सेस में बिलोंग करते हैं, क्योंकि नाइक्विस्ट क्राइटेरिया को ये मीट करते हैं। ठीक है जी? तो अब एक छोटा सा सिमुलेशन देख लेते हैं। सिमुलेशन के लिए लेट मी जस्ट शो यू अ डेमो ऑफ raised cosine filters. It's a small code that I wrote for raised cosine filters, जिसके अंदर आप सबसे पहले हम रेस्ड कोसाइन फिल्टर का जो डिज़ाइन देखेंगे। यहाँ पे मैं आपको ये क्लियर कर दूं कि रेस्ड कोसाइन फिल्टर्स की डेफिनेशन जो यहाँ लिखी जा रही है वो टाइम डोमेन फंक्शन के बारे में लिखी जा रही है। तो जो प्लॉट हम देखेंगे वो टाइम डोमेन फंक्शन के बेसिस पे देखेंगे। अगर हम कोड लिखना चाहें उसके फॉर्म में आपके फिल्टर के लिए, वो भी करा जा सकता है, बहुत बड़ी बात नहीं है, लेकिन हम फिलहाल के लिए जो कर रहे हैं वो आपको बता रहा हूँ। इस कोड के अंदर यहाँ पे 6 अलग अलग वैल्यूज ऑफ रोल ऑफ के लिए डेटा रिप्रेजेंट किया जा रहा है, एंड -10 टाइम से 10 टाइम तक इसकी रिप्रेजेंटेशन रखी जा रही है। तो फिलहाल के लिए ये पोर्शन हमें नहीं चाहिए, तो हम इसको एक बारी ऑफ कर रहे हैं और इसको चेक करते हैं रन करके। राइट, लेट्स हैव अ लुक एट दिस। Let's have a look at this graph, and what you can note is that you can see the legend over here, and the navy blue, the dark blue r is equal to 0 wave is the original sync wave. So what you can note is that the main lobe of this is at the lowest, just by a very small margin, nothing too big, and the side lobes are the largest. You can see that the side lobes have the largest tendencies, right? Similarly, as soon as you go to r is equal to zero point 0.2, that is 20% roll off, this starts to diminish. And you can see the diminishing effect having more pronouncedly in the later sub bands, right? In the later side bands. For r is equal to zero point 0.4, almost the third, even from the second and the third side bands, the data is almost vanished. You can see that if I try to go to the wave over here, it is minus 0.00073, which is a very, very small value. It's a negligible value. And when you go for r is equal to zero point 0.8 or r is equal to 1, what we can observe is that even the very first main lobe is almost negligibly reduced. That means that as soon as you go for higher roll off, what we can see is a practically time limited signal, right? It is practically a time limited signal because even in infinite time, it is not going to have enough energy, it is not going to have enough amplitude to really affect my recovery or my decision making process in any way. And the idea is that essentially I have a very good position, very good disposition already. So there is really no need for consideration of such timelines that exist from minus infinity to infinity, right? Hence, the raised cosine system is very effective in that sense. Notice the problem. The problem is that it is causing a lot of bandwidth issues. So since it is causing a lot of bandwidth issues, there is a main question over here, and the criteria is that the criteria would become that what should we do, uh, basically what can we do to kind of make it a practical scenario, make it a practical solution, and not to waste my bandwidth so much. So is there a way of effective implementation of this strategy such that I use a lower roll off and still I am able to generate stuff which is practical? So hence comes into picture the concept of root raised cosine system, root raised cosine implementations. So let me try to explain that. We noted that h of f is HTF, HCF, HRF, right? So these are the effects of transmitter, the channel, and the receiver. The channel, having said the channel over here, but we can say that there is an assumption of some linear or non-linear effects that the channel is giving up. So obviously, modeling that is going to be a little tougher job. So there is an entire branch of communication which is called equalization. An effectively generated or designed equalizer, what this is supposed to do is that it is supposed to have an effect like this: C divided by some constant divided by HCF. So what that does is when you insert that equalization process before your receiver side, what that is going to do is that it is going to take care of your channel. So let's assume that the channel is taken care of, right? But you are left with this transmitter and receiver. The idea of transmitter and receiver transfer functions is also important in this regard, that HTF is going to generate some sort of pulses for those um, impulse signals that have come in, right? It is going to do something with them. And HRF is supposed to again do something with them, but the end result is supposed to be the HRC, right? The end result is supposed to be HRC. Now, what we have seen is that a raised cosine system essentially looks like a symmetrical wave. It looks like a wave that is symmetrical about zero. And what we require is normally that HTF and HRF, that is the pulse representations via the transmitter and the pulse representations that are going to, or the filtering process of the receiver in itself, they are supposed to be matched together. Remember the logic of match filters. So the order logic of match filter is that if HTF is going to give some sort of pulse shaping, is going to give some sort of shaping, right? Let's say ST to my incoming impulse signal. Then HRF is supposed to be match filter to this, that is a flipped version of this. Since my raised cosine is a symmetrical wave, that essentially means that the flipped version is also going to be the same thing. And hence what we do over here is that we assume that HTF is equal to HRF, hence making this H square F. So the individual representations or implementations of HT and HR are done like under root of HRC, hence calling it root raised cosine. Now, if I call it root raised cosine, it is important to note that individually a root raised cosine is not going to follow Nyquist criteria. Again, let me try to show you. So in this equation, in this same code, if I remove normal and put sqrt, our cost design function is going to generate a root raised cosine system. It is essentially going to be the same thing, the same roll off, the same everything, but it is going to be for uh, a different logic. It is going to be for uh, a different criteria. Okay, so let me try to show you that. So I'm going to run this again, and I would like to share the results. Just a second. So let's first share this screen. Obviously, you can note that this screen is a little bit different. And what we can see is that for different versions of this raised cosine, that is different, what we say as the roll off factors, the wave kind of shifts in such a fashion that the data is not essentially zero at integral multiples of time period. You can see that it is not essentially zero at those time periods. It is going anywhere that it wants, right? It is going anywhere that it wants. So, that being said, the main concern over here is that what happens if I pass one raised cosine filtered system through the same one again? What happens? And that is what happens when you do multiplication of two transfer functions, or convolution in this case of two time domain variables. So what we have done over here is that we have taken convolution of the roll off factor r is equal to zero point 0.4 wave. That is the third wave in the set. And what we have done is that we have taken this sequence, and r is equal to zero point 0.4 representation. What it is doing over here is that between -1 to 1, it is again the similar lobe, right? And what is happening is that it is reducing very fast in comparison to its original shape. It is reducing very fast, and in the third or fourth portions, it has just completely vanished, right? So the practical implementation point of view of root raised cosine kind of gives us a good application based systems. Of course, you but must understand that this is still an estimation. This is still a logic of very truncation, in the sense that you are limiting the data sequence in such a fashion that आपका bandwidth excess यूज हो रहा है, हमें पता है, फिर भी हम उसे यूज कर रहे हैं, और हमें डेटा को कहीं ना कहीं ट्रंकेट करना पड़ जाएगा क्योंकि जब हम उसको यूज करेंगे तो कहीं ना कहीं इंटरसिम्बल इंटरफेरेंस की पॉसिबिलिटी जरूर रहती है, बट इतनी रिड्यूस्ड अमाउंट में रहती है कि वो मैनेजेबल हो जाती है. तो ये है फर्स्ट एस्पेक्ट ऑफ इंटरसिम्बल इंटरफेरेंस एंड द लॉजिक ऑफ raised cosine filters to completely, theoretically completely eliminate the logic of intersymbol interference. Okay. In the next session, in the next video that I'll upload, I will talk about the possibility of duo binary sequencing, and the logic of how some intersymbol interference may be allowed to enter the system, but pre-code it accordingly such that you do not have to worry about it. All right. Thank you, and best of luck.